Welcome to Brain Vision.
Hi everyone, as shown in the figure, gear A having the mass 1 kg and radius of gyration 30 millimeter, that is 0.03 meter. Mass of gear B is given 4 kg and radius of gyration 75 millimeter, that is 0.75 meter. Mass of gear C is given 9 kg and its radius of gyration is 100 millimeter, that is 0.1 meter. Radius of each gear asked are as shown in the figure. The system is initially at rest, so initial velocity or angular velocity is 0. Moment of couple m0 having the magnitude 4 Newton into meter applied on C. There is no selfing occurs between the gears, that is, there is a pure rolling motion. We have to calculate number of revolution required for disk A to to reach angular velocity of 300 rpm. Let us start solving it. First we will calculate moment of inertia of each gear. This problem is based on work energy theorem. So first we are finding moment of inertia of each gear. So calculation of moment of inertia first for gear A. Formula to be used, product of mass into square of radius of gyration. General formula is m into k square. We are using it for gear A. Mass of A is given 1 kg and its radius of gyration is 0.03. So you will get 0.9 into 10 to the power of -3 kg meter square, and that of V would be mass of V is given 4 kg and its radius of gyration is 0.075. So moment of inertia of V you will get 22.5 into 10 to the power -3 kg meter square. Similarly, that of C you will get 9. Mass of C is 9 kg and its radius of gyration is 0.1, so you will get 90 into 10 to the power of -3. Now we will study the kinematics of it. Analysis of kinematics. RA, radius of the gear A is 50 millimeter. Radius of gyration of B, inner and outer two, there are two gears. So For gear V, we have R1 to be 100 millimeter, that is outer one, and R2 50 millimeter. This is for A. And for gear C, radius is RC and it is given 150 millimeter. At a point of contact between gear A and B, we can write R1 omega B, RA omega A. So omega V, you will get RA upon R1. Substituting the value, RA is given 50 millimeter, R1 is 100 millimeter into angular velocity of A. So we will find angular velocity of V is half of angular velocity of A, or you may write 0.5 times A. So this is the one of the relation we have obtained. Similarly, at contact point between gear B and C, we can write RC omega C to be R2 omega B. That is, angular velocity of C will be R2 upon RC into omega V. Substituting the value, R2 is 50 mm, RC is 150, omega V is 0.5 into omega A. So omega C you will get 0.1667 omega A. This is another equation we can consider. Initial kinetic energy is 0. And final kinetic energy of the system would be half IA omega A square, half moment of inertia of V into square of angular velocity of V plus half moment of inertia of C into its angular velocity square. Substituting the value, half you can take common. Moment of inertia of A is 0.9 into 10 to the power minus 3 angular velocity plus half. Moment of inertia of B is given, half I have taken common. So it can be written as 22.5 into 10 to the power minus 3, and omega V is 0.5 times of omega A. IC is 90 into 10 to the power minus 3 into angular velocity of C from equation 2. So on solving this, T2 you will get 4.5125 10 to the power minus 3 into omega A square. Here omega A is given 300 rpm, that is 300 by 60 into 2 pi radian per second. So you will get 10 pi radian per second. Substituting the value here, 4.5125 into 10 pi square. So this energy would be equal to 4.4565 joule. Now you can find the work done. Work done by couple is couple into angular displacement 4 into theta c. Applying work energy theorem, work done is equal to change in kinetic energy solving it, you will get angular displacement of C to be 1.11413. We have to require angular displacement of A. So theta A will be theta C upon 0.116. See the constraint relation for it. That's all for it. Thanks for watching it.